Hello everyone, this is Himang Bora, and today I would be explaining about polynomial regression and the problem of overfitting versus underfitting, and consequently we'll talk about numerical stability, that is choosing Legendre's polynomial or orthogonal basis versus the monomial basis. So for the purpose of explaining this, I have picked up a real world application, that is the prediction of average yield of rice for the state of Assam. So here is the problem statement. So we have been provided with the historical data of the average rice yield in kilograms per hectares of land from reliable government sources from the years 1990 to 2022. And we are going to fit a model to this data point so that we would be able to predict the rice yield for the upcoming years, which would be beneficial for the food and agriculture ministry for the efficient allocation of budget. So our goal is to build a polynomial model T of T that captures the long-term yield trend from noisy yearly observations. As we can see, noise comes from various factors such as weather, climate, government policies, etc. So our model should not be that much sensitive to noise. So let's talk about how it will work. So first, we'll propose a polynomial of degree k, where k is our choice, and try to we'll model the polynomial for k equals to 1 to 20, and then we'll find the best fit for our purpose. Second is the definition of the error function. In our case, we would be using the mean squared error. And third is solving the normal equations, or minimizing the error. That is, the partial derivatives should be equals to 0, and thus we would be solving the normal equations x transpose x times a equals to x transpose t, in which case if x transpose x is invertible, we'll be able to find our coefficients a respectively, a0 to ak respectively. So now let's go to the Python code, which I have written for the demonstration of the same. So firstly, we'll import the necessary libraries. So for the use of Legendre's polynomial, I'm not writing that, and I'm just importing them from the SciPy library. Uh, and these are just for the basic configurations for color and matplotlib. So I'll run this. The libraries are imported successfully. Next, this is the real data set from the official government websites. This data was present in the form of a PDF, so I have hard coded it in a dictionary called yield data, and then I have converted this dictionary into a NumPy arrays. So let me run that. So now, first thing that we would do is we'll visualize the data, that if it is possible to fit a polynomial function through the data. So yes, we can see that this is the data from 1990 to 2022, and we would be trying to fit different polynomials through this data. So these are the helper functions. The first one is to scale, and this scale function would be used for Legendre's polynomial, because as we know that Legendre polynomials are only defined from -1 to 1, and this function Legendre's basis will provide the uh, value of the Legendre's polynomial for the time series and for different degrees. And this is the Vandermonde basis, which is nothing but just the monomial of degree dg. And then this is the fit, which would use linear algebra to fit the model. And this is the root mean square error, which would be used to find this numerical stability. So now we'll try to fit our data for different degree of polynomial. So here I have chosen 3 degrees of polynomial, 1, 3, and 15 for the sake of demonstration, because these are the places where the results are the maximum. So this is the code for plotting this, and when I run this, as we can see that when we are using a linear polynomial to fit the data, uh, the linear polynomial is unable to uh, you know m- find a relation between the points in the past and the future, because linear model is very simple and it is unable to figure out the curvature of the trends. And when we use k equal to 3, and it provides a good fit. In this case also, some of the points do not lie on the curve, but the as a whole, this polynomial captures the trends in the data. And then when we have k equal to 15 or very large polynomial, in this case, the model overfits the data and also the noisy data points, which is not uh, useful, or which is not good for predicting uh, for future. And as it is written here that lower root mean squared error does not mean a better model, we need to always check the fit visually and then consider the context of the data. So now we'll see the training error versus the polynomial degree. So now I'll plot the degree uh, degree versus the error. uh, So as we can see that when we increase the degree of the polynomial, the error uh, comes down because it is fitting the data more accurately, and increasing the degree will increase the curvature of the polynomial, and it would fit the data points more accurately, but it is also fitting the points that are noisy and which do not follow the trend. uh, and so and when we will use this model that overfits, we would make a very wrong prediction for the test data. So we'll use an optical degree that lies between 3 to 5, and that is this that is about this. Now secondly, we'll come to two different types of polynomials, basis functions, that is monomial versus Legendre. So monomial is nothing when but we are using the powers of the input data point, that is 1 t, t square, t cube, etc, etc. But they are very ill conditioned in the sense that higher degrees of uh, the basis, that is when I compare t to the power of, let's say, 99 and t to the power of 100, for t equal to 10, they are approximately same and will be around same. We would see in the future that by plotting these also, that they tend to converge into a same field. And on the other hand, we have Legendre's basis, which are p0 to p k, which is the degree, and these all are orthogonal functions, and uh, and are independent of each other. That's why they are well conditioned. So with the help of a plot, we'll be able to see that. So this is the monomial basis, that is the normal polynomial functions from 1 to t to the power k, and these are the Legendre's basis. And we can see that as the degree increases, for monomial basis, all tend to converge closer to each other. But in the case of Legendre's polynomial, they do not match, and all the polynomials are uniquely shaped. So let's talk about numerical stability now. for numerical stability, we define a condition number k, which measures how sensitive a system is to small perturbations or change in the data set. When the condition number is less than k, the model is well conditioned. Otherwise, it's out of danger zone. And this is we'll see with the help of this code that as we increase the polynomial degree for the Vandermonde or the monomial basis functions, the condition number increases exponentially, while the condition number for the Legendre's polynomial or the orthogonal basis remains constant, because when we'll do the sensitivity analysis or just change data points in our data set, not by very much, we'll see that Vandermonde coefficients swing very wildly or very with a large standard deviation, while the Legendre polynomials coefficient remain stable. As we can see, when we just here we are adding 1% of normal noise to our data set, and we can see that the coefficients from 0 to 11 starts to using the Vandermonde basis, the coefficients are sensitive. That is, they are varying or very much, or the variance is very high. And in the case of Legendre's basis or the orthogonal basis, we can see that the coefficients vary only slightly when we vary the data set. That is because there is as the degree of the monomial basis increases, the correlation between them increases drastically, while the since the Legendre's polynomial are orthogonal to each other, the correlation between them is not that much, as we will see by this graph, this heat map, that when I'm plotting for degree 0 to 10 for the Vandermonde basis as well as the Legendre's basis. So in this case, you can clearly see that the higher degrees of polynomial have higher correlation with each other, while for the Legendre's basis, no, there is slight or minimal correlation between the different bases, because Legendre's polynomial are all orthogonal to each other, or the inner product of any two picked from 0 to 10 in our case would be 0. So final steps are why extrapolation, why overfitting fails. Okay, so we can see that when we overfit our data, and uh, we then try to predict for future, the purple curve is for overfitting the data, and we can see that it predicts a very high value, which would not be the case in uh, the real scenario, while the best fit for degrees equal to 3 to 5, they show a very promising prediction, and or reasonable prediction, and hence we use only smaller or comparable degrees of polynomial, and I have shown using this, I have shown that how to use polynomial regression to model a data with noise, and the difference between the Vandermonde or monomial basis versus the Legendre polynomials and or the orthogonal basis. In which case, we should always prefer Legendre's uh, polynomials as a basis, because they are orthogonal to each other, and as the degree increases, the correlation between the bases is minimal. So that is only written here, and thank you.